Hey guys, we're now into 14.4. We skipped 14.3, so don't worry about that section. But 14.4 is all about what we call implicit differentiation. It's an idea that we're going to use to help us find derivatives when we have multiple variables. Because so far, if I've given you equations that maybe look like one of these three equations, you should be able to find me the derivative fairly easily because they all say y equals, and then on the left side, or excuse me, the right side of the equation, you only have one variable to consider, which were x's typically, right? And so we were able to find the derivative of this first one. We can find the derivative of y with respect to x. Remember, our notation is dy over dx. That's the derivative of y with respect to x. And we can say that the derivative of 3x minus 2 with respect to x should just be a 3, right? We could even do the middle equation. Because it says y equals, and we have an x squared plus x plus 6, we just have x's on that side, then we can find the derivative of y, dy over dx, the derivative of y with respect to x, by taking the derivative of each of these little pieces with respect to x, just that one same variable. So you should end up getting 2x plus 1. Same idea for the third one. We end up getting dy over dx equals negative 3x squared. So all of those we should be able to do because they're what we call explicitly written in terms of one variable. All of them say y equals, and then there's just x's on that other side. But what if I gave you this equation, this 4xy minus 3x equals 6? You see how the x's and y's are kind of all intermingled? It doesn't say y equals. Well, what you would have to do then is you'd have to take that equation and you would have to rewrite it and solve for y. Get it to say y equals. So try it. Try to get that y by itself. I moved my 3x over first, and then I divided both sides by 4x. So now my new equation looks like this, and then the way that we could find the derivative, remember, is what rule? Yeah, well, we'd have to do a whole big old quotient rule, right? Well, what happens then if I give you a little bit more of a complicated problem, like maybe one of these two problems? Holy cow. There's no way that we're going to be able to solve it explicitly for y and get it to say y equals with a whole bunch of just x's, right? These equations are what we call implicit equations. They have x's and y's kind of all intermingled, and we can't get it to look like the way we've been used to. And so there's a new technique that we're going to talk about, and we're going to be able to still find the derivative. We just have to do it implicitly, do implicit differentiation. Okay? So it is useful to use the notation dy over dx instead of just an f prime, so you can kind of see the difference between the relationship of what you're finding the derivative of with respect to what variable. Okay? So in the past, when we've found derivatives, we've been finding derivatives of y as x changes, right? The change in y as x changes. And so when we've been finding the derivative, for example, if I give you this problem, here, we've been finding the derivative of this equation with respect to his variable. Do you see how those two variables kind of match? And so we can find the derivative of x cubed by saying 3x squared and using our power rule. Technically, what we've been doing is we've been finding the derivative of x, the change in x, as x changes. And so you could, if you wanted to, write a dx over dx. But that dx over dx kind of cancels each other out, reduces each other out. And so we haven't been actually writing that last piece there. But compare that to this example where we're finding the derivative of y cubed, but this time with respect to x. And so now you see the difference between the two? The variables there don't quite match. And so when we find the derivative of y cubed, you can still use the power rule and say 3y squared. But what we did, we just found the derivative of y, but with respect to x. So technically, we have a dy over dx behind it, symbolizing that that's what we took the derivative of. And that doesn't go away. That doesn't reduce and kind of cancel out like it did in the first problem. So it's important to keep that dy over dx in my problem. Okay, let's look at a few more and then we'll get a little more complicated as we go. So if I gave you this equation and I asked you to find me the derivative of x plus 3y, I have two separate terms separated by just a plus or minus sign, so we should be able to take the derivative of each piece because it's just separated by a plus or minus sign. If you look at the notation carefully though, we're finding the derivative of this expression with respect to x. So anytime we find the derivative of an x, we can add a dx. If we find the derivative of a y though, we need to make sure that we add a dy over dx. Here we go. So the derivative of x is 1. You could say dx over dx if you want to, and then they would reduce. The derivative of 3y is 3, but be careful, we just took the derivative of a y with respect to a different variable. So now we have a dy over dx. I would probably not write this dx over dx here, and I would just say that my final answer then was 1 plus 3 times dy dx. Okay? All right, look at D. D looks a little bit different. D says I want to find the derivative of this expression with respect to x, but this time I have an x times a y squared. Now be careful, what derivative rule do you think we're going to have to use in order to find the derivative of an x times a y squared? Well, isn't that a product rule? All right, so let's remember product rule. The first times the derivative of the second, so the derivative of y squared with respect to x would be 2y, but remember, we just took the derivative of a y with respect to a different variable, x, so we have to add that dy dx. That's the first times the derivative of the second. Plus, we have the second times the derivative of the first, so the derivative of x is 1, and then you can say dx over dx and reduce it off later if you want to, but I'm just going to not write that and skip that step. Making it look a little bit nicer, I can move this 2 as a coefficient into the front. X, y, dy over dx plus y squared. There is no equal to sign in this problem, so my answer doesn't have an equal to sign. This is just the rate of change of that expression, the derivative of that expression. We'll do some more here in a second where we have some equal to signs. Okay? So practice those, get comfortable with those, and then next video we'll get a little, like I say, funner, right?